Welcome to this online training course, Designing Boards with Intel Agilex FPGAs. My name is Ray Shorten, and I'll be the presenter for this training. This presentation will cover Intel Agilex FPGA products and features, including how-tos and design considerations. Our intention for this course is to help accelerate your learning and development process for your Intel Agilex-based product. By the end of this course, you'll have an understanding of board-level design considerations when designing with an Agilex device. I'll educate you on the tools to help you design the power and thermal aspects of your board and provide information on layout considerations. I'll also point you to some additional resources we have available that will help with the board design. Here's the agenda. First, I'll share some of the new features in the Intel Agilex devices that will make board design with Intel FPGAs easier. This includes changes in the new PDN tool and also some thermal design considerations and solutions. Then I'll talk about some of the new packaging features that will help simplify the layout design. I'll move into some of the tools to help you design for power and thermal considerations, and then wrap it up with some Intel Power solutions to help you with your board design. Now let's take a look at the new power delivery network methodology in Agilex. The device under operation creates noise on all the power rails. This noise causes fluctuation in the supply voltage that can affect the device performance. Some typical performance degradations due to noise include increase in jitter, waveform deformation, and also logic errors. A good power delivery network design is essential for proper device operation. So the PDN becomes more and more challenging as new generations of FPGA devices roll out. And new devices typically require a lower supply voltage, making it even more challenging. New FPGA devices have more logic elements as well. Agilex has very large densities, and more logic elements translates into higher transient current demand. New devices are able to support a higher data rate. The highest data rate supported by the Agilex devices just keeps increasing, making it even more important. Board designers really need to pay more attention to every detail of the PDN design. The good thing is we've made it a lot easier. Here's a slide showing how we used to use the PDN tool to analyze the decoupling strategy and compares it to the new Intel Agilex design methodology. Agilex devices have on-package decoupling caps noted as OPDs and metal insulator metal caps noted as MIMs, M-I-M. MIMs are metal plates separated by a thin layer of silicon oxide. They're typically quite accurate and independent of the voltage. In other words, they're very linear. With these built-in capacitors, the decoupling design methodology changed and has become a lot simpler. For older families, we offered a PDN tool to help determine the number of decoupling capacitors and their values. For Agilex, we have performed the simulations on a more holistic system approach, simplifying the process. The OPDs and the MIMs enable a much simpler design with the ability for us to simulate end-to-end, covering over 95% of typical customer designs. In the end, you'll be able to refer to a static table to determine the number of capacitors and their values for each of the power rails. Here's a slide that shows our power delivery design shift. We've enabled on-package decoupling capacitors on both the LAN side and the die side. We've changed our simulation methodologies where we now have more of a systematic top-down specification from the voltage regulator to the board, to the package, to the silicon, and then also from DC to high frequencies. We have a platform-driven solution in that we have load line recommendation guidelines and systematic VR board design guidelines. Again, essentially, we are simulating from the board level at the output of the voltage regulator all the way to the silicon end to end. As you can see, we've been able to reduce the number of caps down to about 40. There are about 10 of the 0805s, 20 of the 0402s, along with 6 of the 0603s. This is a significant reduction from the motherboard backside cavity decaps from our earlier families. We have performed simulations on the entire system. The first droop is at the C4 bump. C4 stands for Controlled Collapse Chip Connection, which are the bumps between the die and the package. The second droop is at the BGA pins, and then the third droop is at the inductor. So you'll need to merge all three together to get an accurate picture. You can't do it independently. This is what we've done in our simulations. So here's a picture of the voltage droop that we just discussed and the effects of the land side and die side caps. The voltage droop picture on the left shows the top yellow line with 12 land side caps, a droop improvement of 34 millivolts. On each of these on-package decoupling options, either the 12 land side caps or the 18 land side caps with 8 die side caps are implemented based on the package and the die. Some devices incorporate one OPD option. Other Agilex devices may have both. The on-package decoupling reduces the impedance and the voltage droop, enabling us to simplify the PDN analysis. So in summary, with the on-package decoupling caps, we've significantly reduced the number of motherboard backside cavity capacitors. We've also performed a more holistic simulation approach, which replaces the traditional PDN tool. We've performed simulations that cover over 95% of customer use cases. By referring to a static table, you'll be able to easily determine the number of motherboard capacitors and their values to ensure that you deliver clean power to the Agilex device. All of these improvements result in a significant reduction of the number of motherboard decoupling caps for the Agilex devices when compared to the Stratix 10. Next, we'll talk about the thermal design analysis of your Agilex design. Here are the various steps to determining what kind of cooling solution will meet the requirements of your design. First, input your design into Intel's Quartus Prime software. The Power Thermal Calculator, the PTC, which we'll go more in depth later, and the Quartus Power Analyzer, the QPA, will estimate the power your design will consume. They will also estimate the thermal parameters of your design. For step 2, you take these thermal parameters from the PTC or the QPA and intelligently apply it using the compact thermal models that we provide to see what kind of cooling solution requirements your design needs. For step 3, we create and provide the generic models, which allow you to enter in the power distribution numbers from step 2 into the compact thermal model, which generates a case temperature requirement. Then, in step 4, you evaluate the compact thermal model in your system simulation to see whether or not you're going to achieve the case temperature spec. We offer one compact thermal model per package. Then the Power Thermal Calculator allows a generic compact thermal model to be used in such a way that it's specific to your design. The thermal simulation is done using a computational fluid dynamics software cooling package like FlowTherm, IcePack, or Sigma ET. The compact thermal model is a flow thermal plugin, so you basically take the compact thermal model and plug it into the software. Once the simulation is complete, you'll have the operating parameters and temperatures, which will allow you to define the cooling solution, which we'll talk about in the next couple of slides. And then lastly, you'll need to verify the cooling solution. The other new term is SiCA, which defines a total cooling solution to keep the junction temperature at a customer specified operating temperature. It is the slope of the effective thermal resistance. This includes airflow, heatsink, TIM2, which is the thermal interface material 2, which is between the device and the heatsink, and other cooling methods like heat pipes, cold plates, liquid cooling, etc. Agilex PTC will calculate the necessary SiCA value for a customer design. First, customers will enter their design into the PTC along with their target junction temperature and ambient temperature. The PTC will then suggest a SiCA to keep the FPGA at the customer junction temperature. The customer must then design their cooling solution to have a size CA equal or lower than the number from the PTC. One rule of thumb is that as size CA increases, the cooling solution becomes easier. So another way you can quantify your design and take the thermal risks is that you start on the system side to determine the boundary condition characteristics for the FPGA package. The best way to determine that is by using this method here, which is to evaluate how the case temperature changes as a function of different power levels on the package and coming up with the slope and the T ambient effective, which is a y-intercept. This allows you to take all of the system level effects, like all of the power sources in your system. The slope is typically linear because it is a conduction-based approach. The data over a meaningful range of power levels will be linear. Here are some examples of cooling solutions that can be associated with a size CA value. This slide gives a very high-level snapshot of what size CA translates to with input from Intel's packaging team. As you can see, a size CA of 0.3 and above is considered traditional air cooling, while anything below 0.15 move more towards liquid cooling. In reality, your cooling solution will be dependent on what your system is capable of, what are the physical constraints, what is the system environment, how much are you willing to spend on your cooling solution. Moving forward, you'll need to understand these constraints to figure out what's an acceptable size CA value to define your cooling solution. In general, the thermal design of any IC device boils down to the power dissipation and the package thermal resistances. In the case of Agilex, there are different dies in the package which creates a non-uniform power which translates to several power dissipations and several thermal resistances. The goal of design should be to minimize any of these values as much as possible to improve the cooling. Lowering the power, reducing the thermal resistances, lowering the ambient temperature will all have a positive effect on the cooling, and there are techniques to achieve these goals. We help you to provide the tools you need to analyze your cooling solution. Next, we'll talk about some of the changes we've made in Agilex to help simplify board layout and design. We recognize that there are multiple factors that result in PCB design challenges. As we design Agilex, we kept these factors in mind and considered how we can make it easier for our users to design their boards. We understand that you're driven to develop your board in a very short amount of time in a small form factor, focusing on making the design simple and reducing the number of layers, resulting in a lower board cost. As a result, the new Agilex packaging addresses these challenges. One change we made to address these challenges is the ball pattern. We designed the package ball pattern to be in hex pattern. This results in more IOs and transceivers for a given area, enabling more functionality per package area. With the hex ball pattern, we can get 14% more balls in a given area, which enable us to have more transceivers per area versus a standard grid pattern. In the square package on the left, offered on previous families, one full memory channel requires 6 layers of I/O routing deep in the pin field. With the rectangular package in Agilex, one full memory channel requires 1 layer of I/O routing, and the banks are shallow and square, so we can do 4 layers for the entire set of memory. This will help reduce the total number of layers, thus reducing the complexity and the board cost. Although the rectangular package is new to Agilex, it's not new to Intel. Intel has been using rectangular packages since 2008 to help simplify board layout. The hex ball pattern enables us to get more balls per area, which translates into more transceivers per area. That coupled with the rectangular package, we've been able to reduce the number of PCB layers, easing the PCB development effort and lowering the PCB cost. So let's take a look at the tools available to estimate the power and thermal needs of your design. When powering high-performance FPGAs, what will be our biggest concerns and challenges? Well, with increasing device density and higher performance, power consumption considerations are more important than ever. Today's larger devices are able to implement much more of a system's overall functionality, including many high-speed applications that were unheard of only a few years ago. With devices running at higher speeds and performing these more advanced functions, more power is required and consumed. So there are many challenges in regards to power when creating such a design. Early in the design flow, it's necessary to estimate the system power usage to determine the power supply and the cooling requirements. This can be difficult to do, especially with an FPGA design that can change just by reprogramming the device. Supply components must be considered along with the board space required to lay out those components. A cooling solution must be selected and that must be robust enough to prevent thermal damage to the components. With power supplies chosen, the design must stay within a fixed power budget. So going outside of this budget is really not an option since it could require redesigning the power supplies and the cooling solution. And at the same time, the system must meet a cost budget. Bigger power supplies and cooling hardware add to this cost. So if the power usage can be reduced, the overall system cost can be reduced as well. The system must also be reliable. The more fans and the cooling hardware required, the more likely things could fail. And then finally, the design cycle must be as short as possible. Development schedules are tighter than ever, and a lengthy design cycles just to meet the power and thermal requirements is just not acceptable. To meet these challenges, three things are needed. First, you need to close on the design of the system power supplies and the cooling solution as early as possible in the design cycle. This will help speed the overall system closure. Next, you'll need to make sure that the design meets the power budget set for each power supply later in the design flow when the design is near or reaches completion. And then finally, you need to be able to increase the design efficiency and the productivity to shorten the design cycle as much as possible. So what tools can you use to meet all of these needs? Intel FPGA provides the tools you need to close power in your system. At any point in the design cycle, use a power and thermal calculator, or the PTC, to model your power requirements and calculate what kind of cooling solution is required for your design. The PTC is an easy-to-use spreadsheet-like what-if analysis environment that can be used as a standalone tool or while using the Intel Quartus Prime software. With the information reported by the PTC, you can choose and start designing the system power supplies and the cooling solution, meeting the need of having fast system closure. Later in the FPGA design process, use a power analyzer that's built in the Intel Quartus Prime software to generate highly accurate estimates of power usage based on the design's actual resource usage, along with its placement and routing in the device. This helps you meet the second need, meeting the power budget of the design. Finally, use a power optimization advisor along with the automated power optimization options that it suggests to automatically reduce the power usage in your design. These recommendations and options are easy to implement, meeting the third need, which is increasing your overall efficiency and productivity. So just how accurate are the tool's estimates? How confident can you be with the results in making power-related decisions, such as the design of your power supplies? Well, power estimates are only as good as the power models used to describe a device's power usage. To that end, Intel uses a rigorous modeling methodology where detailed circuit models are created using HSPICE. All models are then tested and calibrated against the actual device silicon. To further guarantee the accuracy of the models, power estimates are performed on the models using a variety of actual user designs. Even with highly accurate power models, the power estimates provided by their tools are only as good as the information that is provided to them. For example, Are toggle rates accurate? Does the signal activity information model the real-world operation of your design? And then also, is the count of resource usage, such as the number of logic elements used, accurate for the design? The more accurate the information is, the more accurate the estimates will be. If you are using a device that has final power models, the PTC is expected to provide results within 15% of what you would see for the highest power rails on a real device on a board. This accuracy assumes accurate design inputs have been provided to the tool. The report generated by the tool will include recommended margins for designing your power solution, taking this accuracy into account. For the power analyzer, the results are expected to be within 10%, again, assuming accurate information has been provided to the tool. The PTC allows you to perform early estimates of power even before a project or any design files have been created. If a project is available, accurate information from the project itself can be taken from the Intel Quartus Prime compilation report and entered into the PTC. This provides a more accurate power analysis. Future releases of the Intel Quartus Prime software will be able to generate power-related information for your design that can be immediately imported into the PTC for the most accurate analysis. It is available in two flavors, the Quartus Prime integrated and then also the standalone in both the Windows version and Linux. Some of you may be familiar with the early power estimator known as the EPE, offered from previous FPGA families. For Agilex, we have it integrated into the Quartus, making it much quicker and much more responsive. The PTC can be directly launched from version 19.4 or later of the Intel Quartus Prime software, or run as a standalone Windows or Linux application, avoiding the need for an installation of the Intel Quartus Prime software. In either case, additional licensing is currently required for the tool, so please contact your local FAE for access. You can launch the PTC from within Quartus. Go to the Tools menu, then click on Power and Thermal Calculator. You can also execute Quartus_PTC in Linux, or if you installed the standard PTC, you can just run PTC. And now you're ready to go. The PTC is easy to use. Enter into the tool as much of the listed information as you can. You can enter the information based on your specific requirements and estimated resource usage, or use the values found in the Intel Quartus Prime software compilation report after compiling your design. The more accurate and complete the information, the more accurate the power estimates will be for your final design. As information is entered, report information is generated that provides the estimated power consumption for the device and the design. The calculated information is organized to provide power usage for each type of device resource and power requirements for each supply. As changes are made to the input data, the calculated values update on the fly, providing a true what-if analysis. So let's zoom in on the main tab. Here you can begin to enter the design information. We're not going to go through each of the tabs here because there is an online course on Intel's website that will go through each of the various tabs shown at the bottom. This is just an example to show how the inputs can be modified by you. While resource-specific calculated power output numbers appear on each tab, the easiest way to view calculated power numbers is with the Power Summary window and the Report tab. The Power Summary window displays the power calculated on each of the resource tabs and then sums them up together. This is a quick way of viewing the overall power usage of the design. If you accidentally close the Power Summary window, right-click on the PTC's menu bar to restore it. The Report tab displays the power usage for each required power rail in the design. each rail is broken down into 5 values. There's also a thermal tab that will provide you with the thermal parameters to help determine your cooling solution, which we'll talk about later. For more information on the PTC, there is an online class that goes through each of the different GUIs pages in detail. I just explained one of the 10 tabs to give you a flavor of what to expect in the PTC. So let's take a look at different power supply solutions. Traditionally, devices on a PCB are powered by supplies built from discrete components. Supplies like this typically require a large number of parts to take up valuable real estate on your board. On top of that, more parts means more layout requirements that, if not followed, can lead to problems. Using separate components also means that noisy signals between parts can go into the board, causing issues in other parts of the design if it's not properly isolated. And finally, because traditional discrete parts use a slower switching frequency, they require larger bulk caps and have a slower transient response. So to solve these issues, you can build your FPGA power supply using one or more of the Intel Enpirion Power SoC devices. Power SoCs combine the multiple components of a discrete part power supply into a very small package. By greatly reducing the part count, the supply requires less board space and has a simpler layout. No more internal noisy signals can get injected into the board. Because the Intel Enpirion Power SoC devices switch at a higher frequency, you can use much smaller all-ceramic caps. Typically, when you look at a discrete power supply solution, it looks messy. There's tons of resistors and tons of caps. This is a WYSIWYG of Intel Enpirion's power solution. What you see is what you get. Intel Enpirion's solution is very dense, very small, and very simple. For this integrated solution, you'll need a couple of input caps, a couple of output caps, and maybe 2 resistors. Again, it's very simple. It's as easy as designing an LDO, but you get all the benefits of a switch mode power supply. Here's a visual of the complete solution. No other components are necessary to operate with our integrated modules. Again, it's very simple, very straightforward. Other vendors may require you to do 2 to 3 times the amount of components because you have to do all of the compensation externally. Intel's Enpirion solution is all integrated. It can be your solution for power requirements up to 80 amps. Now for power requirements above 80 amps, you'll need to incorporate a discrete solution. Unfortunately, it is not cost-effective to create an integrated package for currents that high. Not only is it not cost-effective, but it's also very difficult to design with the temperature challenges created in a single package. The first discrete high current power solution will consist of the Intel Enpirion ED8401 4-phase digital controller paired with 4 of the Intel Enpirion's ET6160 60 amp power stages, which has an integrated driver. This solution will enable designers to take advantage of the excellent performance in accuracy, ripple, and transient response that a digital control architecture enables, while achieving a smaller and more power-dense footprint that is more flexible and scalable to higher power. Both the 8401 and the 6160 are released today. PWM 1, 2, 3, and 4 are clock signals that feed the power stage, and in this example, they're 90 degrees out of phase with each other. TSEN is a temperature sense, and ISEN is a current sense feeding back to the controller. If you don't need as much current, you can use it as a 2-phase or 3-phase controller as well. If it's a 2-phase, then the PWM clock signals will be 180 degrees out of phase with each other. You can get the full reference design online or from your local power FAE specialists. In the picture, you can see the controller on the left feeding the 4 FETs, and then the 4 FETs feed the inductors because you have to be able to store those voltages in between switching nodes. This picture is straight from one of our dev kits, so it's a real-world example. Again, You can have 2, 3, or 4 phases delivering up to 240 amps peak. V-out accuracy is impressive at 0.5% set point accuracy, while the ripple is less than 10 millivolts peak to peak. I'm showing what we call the hero product list. It is a simple list for your reference. It is intended to make it simple and easy to select your power solution. Determine your current requirement with the power and thermal calculator, and then look up the part in this cross-reference table. It's that easy. If your requirements are greater than 80 amps, then you'll have to consider a discrete solution that we talked about a few slides ago. Here's the Enpirion Power new product roadmap. You can see we're investing in the higher current solutions with 60 amp devices and also with an 8-phase digital controller. As you can imagine, there's a lot of ICs out there that we can power, not just an FPGA. And these other ICs consume a lot more power than an FPGA does. We're not getting out of the integrated module business. We'll continue to invest in this space with the power SoC modules, as shown here with the EN2840/60 12 volt, 4 amp, and 6 amp modules, which are on the roadmap. As you can see, we have a comprehensive selection of devices. It's a very powerful story. Here's a customer example of our discrete solution. It's a real solution shipping to our early access partners. It's been fully tested and vetted by us and by our customers and is expected to be released soon. On the Intel website, you can purchase the interposer board and then connect it up to your board. It will allow you to connect the Generation 5 VR test tool to vet out your power supply. You should be able to reach out to your local FAE power specialist for one of these. Each power specialist has what we call a VRTT, a voltage regulation test tool. They can visit you in your lab, connect it up, and inject large loads to see what your power supply transient response is. It'll measure the ripple voltage and then also the DC voltage accuracy. There are a suite of software tests, and once it's set up, you can completely characterize your whole power supply in 30 minutes. The VRTT mimics your FPGA and tests your power supply. You can also borrow them for up to 2 months. Just go online at the Intel store to request a VRTT. Power verification is also available through our FAE power specialists. They have a scope and will travel. They can come visit you on site and head into the lab with their tools to measure the DC accuracy, measure the ripple noise, measure the transient response, and verify the power sequencing. This usually takes about 4 hours to complete. So talk to your local FAE if you're interested, and they'll be able to get you in contact with the FAE power specialist. Well, every device family has its own device handbook. It's often helpful during board development to have a detailed pinout table for a particular device. You can find detailed information about device pinouts for every device in every device family at the first link. Verifying pin connections prior to committing to hardware is a critical step that will help reduce the chance of needing a board respin. The pin connection guideline documents, also linked here, should be read and followed when you develop your pinout and when you review your pinouts prior to the final layout of your board. And then lastly, we always recommend that you generate an example design with all the IOs and the clocks defined in Quartus. Using the latest version of Quartus will help check to make sure that there's no pin violations to help ensure the success of your Agilex design. Intel FPGA provides schematic review worksheets for each device family intended to help you find mistakes in your schematic and adhere to design guidelines. These worksheets are based off of the respective device pin connection guidelines and other reference literature applicable to board level pin connections that need to be considered when you finalize your schematic. Intel FPGA also provides a layout review worksheet intended to help you find mistakes in your PCB layout. This worksheet is based on guidelines that can be found at the Board Design Resource Center and other reference literature applicable to board layout techniques and practices that need to be considered when you finalize your PCB layout. All worksheets are available in Word doc format, allowing for easy editing and entering of information for your design. If you would like to continue your learning of the Intel HyperFlex devices, you can search for free online and instructor-led training using the links here. To learn more about Intel Agilex FPGAs and SoCs, visit the Intel Agilex device page at intel.com. There you can download the Intel Agilex device overview document, which provides you detailed information of Agilex devices and its capabilities. You can also download the logic array and ALM user guide. Additionally, don't forget to watch a set of demo videos of Intel Agilex devices in action while you're on that page. We also encourage you to try Intel Agilex devices on Quartus Prime Pro for a limited time. To do so, contact your local sales and FAEs or send a message to agilex_webinars at intel.com to request for Intel Agilex software access and mention the access code written on this slide. Finally, as I mentioned earlier, this webinar is the second of a series of Intel Agilex monthly webinar series. We have a new webinar series coming up that will cover Intel Agilex features in greater details, including how-tos and design considerations. To learn more about future webinars, visit the Intel Agilex webpage at intel.com. That page will regularly be updated as schedule and registrations of the new webinars become available. I hope you learned some valuable information about the power thermal calculator, some of the power solutions that we offer, and how to ensure that the power delivery network is clean. We also talked about how to analyze the thermal challenges and understand some of the new packaging features to reduce layout complexity. We do have a lot more in-depth information on Intel's website. I encourage you to visit the board developer section in the Programmable Solutions group part of the website. This concludes this webinar. Again, my name is Ray Shoughton. Thank you for your time.